Detroit, Michigan, the spring of 1985. A plant engineer at a mid-size automotive supplier sits at his desk with a specification sheet in front of him. He has been buying Cincinnati Milacron machines for 30 years. His shop floor runs on them. His machinists were trained on them. The green chip guards the black cast iron ways, the achromatic control panel. These are not unfamiliar objects to him. They are the furniture of his professional life. He picks up his pen. He fills in the machine Cincinnati Milacron Machining Center. He fills in the table size, the spindle taper, the coolant system. Then he reaches the controller line. He writes FANUC, not achromatic, not Cincinnati's own control system, the system that Cincinnati Milacron had spent 20 years and tens of millions of American engineering dollars developing, refining, and teaching to American machinists from Detroit to Los Angeles. The system, whose programming language was written in Cincinnati, Ohio by American engineers who had given their careers to making it the standard of American CNC practice. He writes FANUC, the Japanese competitor's electronics, and sends the order in. He was not the first. By 1985, he was not even unusual. Across American machine shops, across automotive suppliers, across aerospace subcontractors, and job shops and tool rooms from Ohio to California, plant engineers were doing exactly the same thing. They wanted the Cincinnati machine. They specified the Japanese controller. And Cincinnati Milacron, because it needed the orders, was filling those specifications, installing a competitor's brain into its own body, and shipping the result out the door. By 1985, FANUC controlled more than 50% of the world's CNC controller market. Cincinnati Milacron's achromatic, developed at a cost the company had never fully recovered, was losing specification battles in its own home territory, in the industrial Midwest, in the American machine shops that Cincinnati had supplied since before any of those plant engineers were born. Here is what makes that specification sheet something other than a routine purchasing decision. 25 years earlier, in 1960, Cincinnati Milacron had stood at the International Machine Tool Show in Chicago and demonstrated to the American manufacturing industry what computer numerical control could do. The machine was called the Cintimatic. It was the first CNC machining center ever shown to American industry. Cincinnati Milacron did not adopt CNC. Cincinnati Milacron introduced it. The company that showed America what CNC was, that stood on the floor of McCormick Place and proved that a machine could hold a program, execute a sequence, and hold tolerance without a machinist turning a handle, was now watching American shops write a Japanese controller brand into their purchase orders for Cincinnati machines. The pioneer was being displaced by the technology it had pioneered. But the real story of Cincinnati Milacron is not the specification sheet in a Detroit machine shop. It is not the FANUC controller or the achromatic program or even the leveraged buyout that would arrive 12 years later and end the company as an operating enterprise. The real story is what Cincinnati Milacron built over 113 years, the machines, the industry, the professional infrastructure of American manufacturing precision, and what it took to bring all of it down. Every week we tell the stories of the American companies that built the machines the factory ran on and what the market did to them. If that history matters to you, if you ran one of these machines, worked alongside one, or simply want to understand what American manufacturing was and what it became like, the video and subscribe. The story begins not in Japan, not in a boardroom on Wall Street, but in Cincinnati, Ohio in 1884. Cincinnati, Ohio in 1884 was not a quiet city. The Mill Creek Valley, the industrial corridor that ran southwest from the city center toward the Ohio River, was already one of the densest concentrations of American manufacturing in the country. Soap factories, iron foundries, brewing operations, carriage works. The smell of coal smoke and hot metal was not occasional. It was permanent. The valley ran on it. It was into this environment that a group of Cincinnati machinists and investors incorporated the Cincinnati Milling Machine Company in 1884. The principal figure in the founding was Frederick A. Holtz, a trained machinist who understood with the precision that only someone who had stood at a machine and held a cut all day could understand exactly what American factories were missing. What they were missing was a milling machine built to production tolerances. The milling machine, a machine tool in which a rotating multi-tooth cutter removes metal from a workpiece clamped to a moving table, was not a new invention in 1884. American factories had been using milling machines in various forms since the Civil War era. But the machines available to American manufacturers in the 1880s were inconsistent. They were accurate enough for light work, slow work, one-off work. They were not accurate enough, durable enough, or fast enough for the kind of production that American industry was beginning to demand. The American economy of the 1880s was accelerating in a specific direction, interchangeable parts at volume. The bicycle boom was coming. The sewing machine industry was already there. The typewriter was arriving. Small arms manufacturing, which had pioneered interchangeable parts production at the Springfield Armory in Massachusetts, was setting the precision standard that every other American industry would eventually be measured against. All of these industries needed a milling machine that could hold a dimension shift after shift, part after part, without constant operator adjustment, and without rebuilding the machine every 2 years. The Cincinnati Milling Machine Company was founded to build that machine. The early products were plain milling machines in which the spindle axis ran horizontal parallel to the table and the cutter engaged the workpiece from the side or top as the table fed the work forward. Plain and straightforward in concept, extraordinarily difficult to build to consistent tolerance in practice. The accuracy of a milling machine's cut is only as good as the accuracy of its spindle, its table ways, and the rigidity of every casting that holds them in alignment under cutting load. Getting all three right consistently at a price an American factory could afford was the problem Holtz and his partners set out to solve. By the early 1890s, they were solving it. The Cincinnati plain milling machine began appearing in American factory catalogs and Thomas Register listings in the 1890s at prices that records of the period suggest ran between $350 and $500 for a standard production model, the equivalent of approximately $12,000 to $17,000 in current dollars. It was not a cheap machine. It was not intended to be. It was intended to be the machine that held tolerance when cheaper machines would not ran production, when lesser machines required constant attention and lasted 20 years when the competition lasted 5. The American market's first significant institutional validation came from the U.S. government. When the United States entered the First World War in 1917, the Army Ordnance Department required a rapid and massive expansion of American small arms production. The Springfield Armory in Massachusetts and the Rock Island Arsenal in Illinois, the two primary government arsenals, needed milling machines that could produce rifle components to ordnance tolerances in volume on a production schedule that left no room for machine downtime. Cincinnati Milling Machine Company received contracts for both facilities. The machines shipped. They ran. They held the tolerances the government required. That contract was not simply revenue. It was certification, the institutional stamp that told every private American manufacturer that the Cincinnati machine was what the U.S. government trusted when precision and production reliability were not negotiable. The company that left the Mill Creek Valley to supply the Springfield Armory in 1917 was no longer a regional machine tool builder feeling its way through a crowded market. It was the emerging standard of American milling machine practice. And the factory at Columbia Parkway, the campus along the Mill Creek Valley that would eventually employ 15,000 Americans at its peak, was already beginning to grow. What grew with it was something harder to measure than revenue or employment: a reputation. In American machine tool practice, reputation accumulates slowly and is defended obsessively. A machinist who ran a Cincinnati machine in 1910 told the apprentice who sat up next to him that the Cincinnati held tolerance. That apprentice told the plant foreman who hired him in 1925. The foreman told the purchasing manager who signed the specifications for the new plant in 1938. Reputation in American manufacturing does not travel through advertising. It travels through the shop floor, shift by shift, generation by generation. By 1920, the Cincinnati Milling Machine Company had that reputation. The question that would define the next 60 years was how long a reputation built on mechanical precision could protect a company in a world that was about to discover that precision could be achieved by other means entirely. That answer would not come for 40 years, but when it came, it would come from Cincinnati Milacron itself. By the 1930s, the Cincinnati plain milling machine had become something that American industry rarely bestows on any product, a default assumption. When an American plant engineer in 1935 needed a milling machine, he did not begin his evaluation with an open field of candidates. He began with the Cincinnati. If the Cincinnati could do the job, and in most cases it could, the evaluation ended there. Other machines existed. Other builders had catalogs. But the Cincinnati was the machine that American tool rooms had standardized on, the machine that American machinists had been trained on, the machine whose tolerances American blueprints were written to accommodate. The Cincinnati No. 2 and No. 3 plain milling machine series of the 1930s represented the mechanical peak of what the company had been building toward since 1884. Cast iron column and knee construction, the column being the vertical backbone of the machine, the knee being the vertically adjustable support that carries the table ground to surface accuracies that held table flatness to 1/2 of 1/1000th of an inch per foot of travel. The table itself moved in two horizontal directions, left and right, and in and out, presenting the clamped workpiece to the rotating cutter with a repeatability that an experienced machinist could trust without measuring every part. The machine weighed 11 tons. It did not move when the cutter engaged. That was the point. At approximately $3,500 for a standard No. 3 configuration, in 1935 the equivalent of roughly $78,000. Today, the Cincinnati milling machine was not purchased casually. It was purchased by plant engineers who had calculated what a machine failure cost per hour of downtime, what a tolerance failure cost in scrapped parts, and what 20 years of reliable production was worth against the price of a cheaper alternative that would require rebuilding in 5. The Cincinnati won that calculation consistently. No Japanese equivalent existed at any price. No German equivalent was available in the American market at scale. The Cincinnati was what American factories ran on, and American factories knew it. Then the Second World War arrived, and everything the Cincinnati Milling Machine Company had built for 50 years was tested at a scale its founders could not have imagined. When the United States entered the war in December 1941, American manufacturing faced a production requirement that had no historical precedent. Aircraft, tanks, ships, artillery, small arms, engines. Every one of these required machined metal components. Every machined metal component required a machine tool. And the machine tool that American factories relied on, the machine tool that was already in place, already in production, already trusted by the engineers who ran the plants, was the Cincinnati milling machine. Boeing's plant in Wichita, Kansas, producing B-29 Superfortress bombers for the Army Air Forces, ran Cincinnati milling machines on wing spar production. The wing spar, the primary structural member that carries the load of an aircraft's wing, had to be milled to dimensional tolerances that, if missed, meant an aircraft that could not fly safely. The machines holding those tolerances were built in Cincinnati, Ohio. The Pratt & Whitney aircraft engine plant in East Hartford, Connecticut, producing the R2800 double wasp radial engine that powered the F-4U Corsair, the P-47 Thunderbolt, and the B-24 Liberator, ran Cincinnati milling machines on engine case and cylinder head production. Every engine that left that plant had been shaped in part by a Cincinnati machine. General Motors' Willow Run plant in Ypsilanti, Michigan, the facility that Henry Kaiser's engineers converted to produce B-24 Liberator bombers at a rate that astonished American production planners, equipped its machining operations with Cincinnati equipment on production lines that had no margin for machine failure. The U.S. Army Ordnance Corps, the U.S. Navy Bureau of Ordnance, Douglas Aircraft in Long Beach, North American Aviation in Inglewood, the machine that was already the default assumption of American manufacturing in 1935, became by 1943 the machine that American war production ran on. Peak wartime employment at the Columbia Parkway campus exceeded 10,000 workers. The plant ran 3 shifts. It ran on Sundays. The waiting list for a new Cincinnati milling machine at the height of wartime production demand ran to 18 months. That was the mechanical peak. That was what 50 years of reputation, 50 years of tolerance, 50 years of the Mill Creek Valley's accumulated manufacturing craft had built. But 1945 was not the end of the story. It was the hinge point, because in the decade after the war, something was happening in American laboratories and American defense research facilities that would eventually make everything the Cincinnati Milling Machine Company had perfected: the cast iron column, the precision ground ways, the table that a machinist moved by hand and held by feel, not obsolete exactly, but insufficient. Insufficient for the parts that American aerospace and defense programs were beginning to require. Parts with contours that no human hand turning a crank could accurately produce. Parts with three-dimensional surfaces defined by mathematical equations, not by a blueprint dimension a machinist could measure with a micrometer. The answer to that insufficiency was developed at the Massachusetts Institute of Technology under contract to the U.S. Air Force between 1949 and 1952. It was called numerical control, NC, a system in which a machine tool's axis movements were directed not by a machinist turning hand wheels, but by a program, a sequence of numerical instructions encoded on punched paper tape, fed through a reader attached to the machine, translated into electrical signals that moved the axis automatically. The machinist did not turn the handle. The tape moved the machine. The implications for American manufacturing were profound. An NC machine could produce a complex contoured part, a jet engine blade, an aircraft structural component, a die surface that would have required hours of skilled handwork on a conventional machine. The NC machine produced it from tape repeatedly to the same dimensions at a speed no human operator could match. Cincinnati Milling Machine Company understood what NC meant faster than almost any other American builder. And in 1960, at the International Machine Tool Show at McCormick Place in Chicago, the biennial trade exhibition where American machine tool builders launched products and competed for the orders of American plant managers, Cincinnati Milling Machine Company demonstrated something that no American company had shown before. They called it the Cintimatic. The Cintimatic was not simply an NC machine. It was a machining center, a single machine capable of milling, drilling, boring, and tapping a workpiece in a single setup, automatically changing its own cutting tools from a carousel as the program commanded. A part that previously required 4 separate machine setups, 4 separate fixturing operations, 4 opportunities for accumulated dimensional error could now be completed in one. The program loaded. The tools changed automatically. The part came off complete. The Cintimatic, listed at approximately $65,000 to $80,000 in 1960, the equivalent of between $680,000 and $840,000 today. There was no comparable American machine at any price. There was no comparable machine anywhere in the world at any price. Cincinnati Milling Machine Company had not adopted the future of American manufacturing. It had built it, priced it, and put it on the floor at McCormick Place for every American plant engineer to see. The controller that ran the Cintimatic was Cincinnati's own. They called it the Achromatic. It was a proprietary CNC system, CNC standing for Computer Numerical Control, the evolution of NC, in which an onboard computer replaced the paper tape reader, stored programs internally, and allowed editing and modification at the machine itself. The Achromatic's programming language was written by Cincinnati engineers. Its interface was designed for American machinists. Its field support was provided by Cincinnati application engineers who could arrive at a customer's plant program apart from a blueprint, prove the process, and hand it to production all in a single day. No Japanese builder, no German builder, no competitor of any nationality could provide that level of field support in the American market in 1960. The Achromatic was not just a controller, it was a service infrastructure. It was the reason American shops that bought a Cincinnati CNC machine stayed with Cincinnati when the next machine came due. The endorsements followed the capability. The U.S. Air Force standardized Cintimatic machining centers for complex aerospace component production. Pratt & Whitney specified Cincinnati CNC equipment for jet engine component machining. Boeing evaluated and adopted Cincinnati machining centers for airframe structural work. The same institutional network that had trusted the Cincinnati plane milling machine in 1935 and 1943 trusted the Cintimatic in 1962. The nameplate on the column was not a city of origin. It was a tolerance standard. And in 1970, the company that had operated as the Cincinnati Milling Machine Company for 86 years renamed itself to reflect what it had become. Not a milling machine builder, a full-spectrum manufacturing technology company. The new name carried the old city and a new ambition. Cincinnati Milacron. The name change was not cosmetic, it was a declaration. The company that had defined American milling machine practice for nearly a century was announcing that it intended to define something larger, the future of American manufacturing technology itself. For a moment, for a remarkable, specific, quantifiable moment in American industrial history, that declaration was not arrogance, it was accurate. In 1974, Cincinnati Milacron did something that no American manufacturing company had ever done. It sold a robot, not a prototype, Not a laboratory demonstration, not a government-funded research exhibit at a trade show. A commercial product with a price, a delivery date, a warranty, and a field service organization that would install it, commission it, and support it in a customer's plant. The machine was called the T3, the Tomorrow Tool. It was a 6-axis articulated arm roughly the size and reach of a human arm, extended from a fixed shoulder, controlled by a Digital Equipment Corporation mini-computer the size of a refrigerator. It could be programmed to perform spot welding, spray painting material, handling and assembly operations, repeating its programmed motion path to an accuracy of plus or minus 0.05 of an inch, shift after shift, without fatigue, without variation, without a coffee break. General Motors was the first major customer. GM's manufacturing plants installed T3 robots on body welding lines, where the robot's precision and repeatability in positioning a spot weld electrode replaced an operation that had previously required a human operator working in conditions, heat sparks, noise, repetitive strain that no labor agreement could make comfortable. The T3 did not replace skilled machinists. It replaced the most physically punishing work on the factory floor. And it did it better. The American manufacturing press took notice immediately. Cincinnati Milacron was not a robot company. It was a machine tool company that had looked at the trajectory of American manufacturing, rising labor costs, increasing part complexity, growing pressure from foreign competition, and concluded that the factory of the future would not be run entirely by human hands. The T3 was the company's answer to that conclusion. It was also, in retrospect, the most far-sighted product decision Cincinnati Milacron ever made, and the most complicated one. But before the complication arrives, the scale of what Cincinnati Milacron had become by the mid-1970s deserves to be stated plainly, because it is easy to lose in the narrative of eventual decline. At its peak in the mid to late 1970s, Cincinnati Milacron was the largest machine tool builder in the United States and one of the largest in the world. The Columbia Parkway campus in Cincinnati, the complex of manufacturing buildings, engineering offices, and test facilities strung along the Mill Creek Valley employed 15,000 people, 15,000 Americans who designed machines, cast iron groundways, assembled spindles, wrote CNC programs, tested tolerances, sold to plant engineers, and serviced equipment in customer facilities across the country. Annual revenue peaked at $1.2 billion in 1978. In an industry where most competitors measured their revenues in the tens or low hundreds of millions, $1.2 billion was not a large company. It was a dominant one. The authorized machine tool dealer network that represented Cincinnati Milacron across the United States numbered more than 200 firms at peak. These were not catalog order takers. They were application engineering organizations staffed by technical salespeople who understood machining processes, who could walk into a plant, analyze a production problem, specify the correct Cincinnati machine and tooling configuration, and prove the solution before the purchase order was signed. The knowledge embedded in that dealer network, the accumulated process engineering expertise of 200 organizations operating in every industrial market in America, was not a distribution channel. It was a professional infrastructure. It had taken 40 years to build. In American defense and aerospace manufacturing, Cincinnati Milacron's equipment was not optional equipment. It was specified equipment. The U.S. Air Force's production facilities for the F-15 Eagle fighter, McDonnell Douglas in St. Louis, ran Cincinnati Milacron machining centers on airframe structural component production. The titanium bulkheads, the wing carry-through structure, the fuselage frames that gave the F-15 its strength-to-weight ratio. These were machined on Cincinnati equipment. Titanium is among the most difficult metals to machine. It work hardens rapidly, it generates heat that destroys cutting tools, and it demands rigidity from the machine that lesser equipment cannot provide. Cincinnati Milacron's machining centers provided it. Pratt & Whitney's facility in East Hartford, Connecticut, now producing the F-100 turbofan engine that powered the F-15 and F-16, specified Cincinnati Milacron machining centers for turbine blade and compressor disc production. The tolerances on a jet turbine disc, the component that spins at tens of thousands of revolutions per minute and holds the turbine blades against centrifugal forces that would tear a lesser component apart, are measured in 10,000ths of an inch. Cincinnati Milacron's equipment held them. General Dynamics in Fort Worth, Texas, producing the F-16 Fighting Falcon fuselage, ran Cincinnati machining centers on aluminum structural production. Rockwell International's B-1 bomber program before its cancellation in 1977 and reinstatement in 1981 had specified Cincinnati equipment for composite and metal structural machining. Lockheed's facility in Burbank, California, producing the S-3 Viking and later components for classified programs, was a Cincinnati Milacron customer. In American automotive manufacturing, still the single largest buyer of American machine tools in the 1970s, Cincinnati Milacron's presence was equally foundational. General Motors engine plants across Michigan and Ohio ran Cincinnati machining centers on cylinder head and engine block machining operations. Ford's powertrain manufacturing facilities in Romeo and Windsor were Cincinnati customers. Chrysler's manufacturing engineering department specified Cincinnati equipment for its transmission production lines. The American machine tool dealer who represented Cincinnati Milacron in Detroit did not call on purchasing departments. He called on manufacturing engineering departments, on production superintendents, on chief engineers. Because the decision to buy a Cincinnati machining center was not a purchasing decision. It was an engineering decision made by people who understood what the machine could do and what the alternative cost in terms of scrapped parts, production downtime, and the slow erosion of tolerance that characterized cheaper equipment running at the limits of its capability. And at the center of all of it, the aerospace programs, the automotive plants, the defense facilities, the job shops, the tool and die operations, was the Achromatic CNC controller. By the late 1970s, the Achromatic was the CNC programming language that American machining programs were written in. Community colleges in Ohio, Michigan, and Indiana were teaching Achromatic programming in their machining technology curricula. American machinists who had learned to program on an Achromatic controller could walk into any Cincinnati Milacron customer's facility in the country and be productive from their first shift. That was the moat. Not the cast iron, not the precision ground ways, not the spindle bearings hand-fitted to 10,000ths of an inch. The moat was the Achromatic. It was a programming language spoken by an entire professional generation of American machinists, and it ran exclusively on Cincinnati machines. In 1978, Cincinnati Milacron shipped $2 billion in machine tools, robots, and plastics processing equipment from its Columbia Parkway campus. The plants had not changed. The orders were about to. Before the numbers change, and they are about to change in ways that cannot be explained by any single decision or any single competitor, it is worth stopping on the Columbia Parkway campus in the late 1970s and simply being present in it. Because the audience watching this video did not experience Cincinnati Milacron as a revenue chart. They experienced it as a machine. If you ran a Cincinnati milling machine, if you set up a job on one, if you made your first cut on one, if you spent the better part of a career standing next to one, you did not need a balance sheet to understand what the company was. The machine told you everything. The Cincinnati knee mill powered up with a sound that experienced machinists described not as noise but as confirmation. A low, steady hum from the spindle motor coming up to speed, not the thin, high-frequency whine of an underpowered machine working at its limits, but the deep, even tone of a motor with reserve capacity, a motor that was running comfortably at the load you were asking of it. That sound meant the machine was right. That sound meant the setup was solid and the cut was going to be clean. The hand wheels on a Cincinnati milling machine moved with a resistance that took new operators by surprise. Not stiffness resistance. Precision ground lead screws turning in preloaded nuts geared through an apron that had been assembled and adjusted by hand in Cincinnati before the machine ever left the factory. When you moved the table on a Cincinnati, you felt the lead screw. You felt the nut. You felt the table move. An experienced machinist did not look at the dial to know where the table was. He felt it. The lead screw resistance told him. The flood coolant soluble oil mixed with water pumped over the cutter and the workpiece at a rate calibrated for the material, and the cut had a smell that no machinist who worked in a Cincinnati shop has ever entirely forgotten. Metallic, slightly sweet from the oil, cut through by the sharper smell of the metal itself, different for aluminum than for steel, different for cast iron than for either. The coolant smell was the smell of production. It was the smell of parts being made to print shift after shift in a shop that knew what it was doing. The chip coming off a correctly running Cincinnati face mill had a specific character, a continuous tightly curled spiral blue at the tip where the heat of cutting had oxidized the steel silver where it had cooled, landing in the chip pan in a coil that a machinist could read like a diagnosis. A chip that curled correctly meant the feed rate was right, the cutter was sharp, the coolant was doing its job, and the machine was holding the cut without chatter. Chatter, the vibration that occurred when the machine's rigidity was insufficient for the cutting load, or when the setup was wrong, or when the tool was dull, produced a sound that every machinist recognized instantly. A screech or a harmonic vibration you felt in the floor before you heard it clearly. You stopped the cut. You found the problem. You reran the setup. On a Cincinnati, chatter was the exception. On lesser machines, it was negotiated with. That was what 15,000 Americans built on the Columbia Parkway campus in the late 1970s. Not a product, a standard. Yeah. A standard of what American manufacturing precision felt like when it was working correctly. When the spindle was true, the ways were flat, the lead screw was tight, and the achromatic controller was executing a program that an American machinist had written from an American blueprint in an American shop. The stakes of losing that standard were not abstract. They were physical. They were measured in the parts that would or would not hold tolerance when the Cincinnati was gone and something else took its place. In the summer of 1943, the Cincinnati milling machines running at Boeing's Wichita plant were producing wing spars for the B-29 Superfortress, the bomber that the Army Air Forces was building to carry the war to the Japanese home islands. The wing spar of a B-29 ran 63 feet from root to tip. Its dimensional tolerances were held to 0.02 of an inch along its full length. 0.02, the width of a human hair split in half. The machines holding that tolerance were built in Cincinnati, Ohio by American workers who understood that the accuracy of their work was not an abstraction. It was the structural integrity of an aircraft that American crews would fly over the Pacific at 30,000 feet. The symptomatic machining center that Cincinnati Milacron demonstrated at McCormick Place in 1960 could produce automatically and repeatably the kind of complex three-dimensional components that the aerospace programs of the 1960s were beginning to require in quantities that no conventional machine shop could meet. The F-4 Phantom's airframe structural components, the Saturn V rocket engine's turbopump housings, parts whose contours were defined by equations, not by dimensions a machinist could check with a micrometer. Cincinnati Milacron did not simply sell machines to those programs, it made those programs manufacturable. There is a difference. A program that cannot be manufactured does not fly. A rocket that cannot be built does not leave the ground. The machine that makes the part possible is not a supporting player in that story. It is a precondition of it. By 1978, Cincinnati Milacron was not just the largest American machine tool builder. It was the institutional memory of American manufacturing precision. The company whose equipment, whose controllers, whose application engineers, and whose dealer network constituted the working knowledge of how American factories made things to tolerance. That institutional memory was worth $1.2 billion a year in 1978. By 1988, it was worth $400 million. The plants had not changed. The orders had. And the reason the orders had changed was not a mystery, and it was not a surprise, and it was not, if the records of the period are read honestly, something that Cincinnati Milacron did not see coming. The company saw it coming, it responded. The response was not enough. The story of why it was not enough is the story of 5 forces converging on one American company in the space of 15 years. And what happens to an institution when the world it was built to serve stops being the world that exists? The first warning arrived not as a crisis, it arrived as a statistic. In 1975, the National Machine Tool Builders Association, the NMTBA, the trade organization that had tracked American machine tool production and imports since 1902, published its annual statistical report. The import line item for Japanese machine tools, which had been a minor footnote in the early 1970s, had grown. Not alarmingly, not yet. But the direction was clear, and the engineers and executives at Cincinnati Milacron who read the NMTBA report understood what a direction meant when the underlying economics were structural. Japanese machine tool builders, Yamazaki Mazek Morisaki, Okuma Makino had spent the late 1960s and early 1970s building CNC machining centers and CNC turning centers under the coordinated development support of Japan's Ministry of International Trade and Industry, the agency known as MITI. MITI had identified machine tool manufacturing as a strategic industry, had organized cooperative research programs among Japanese builders, had provided export financing and pricing support, and had in effect applied the resources of the Japanese government to the problem of competing with American machine tool builders in the American market. The result entered American distribution in the mid-1970s at prices that American builders could not match without losing money on every machine they shipped. In 1975, Japanese builders held under 10% of the American CNC machining center market. The number was not threatening in isolation. But the NMTBA economists who modeled the trajectory understood the implication. If the price differential was structural, if it reflected not a temporary export promotion, but a permanent cost advantage built on lower Japanese wage rates, government-coordinated R&D and the scale economies of a builder producing for both the Japanese domestic market and the American export market simultaneously, then 10% was not a ceiling. It was a starting point. Cincinnati Milacron's internal response in 1975 was awareness without alarm. The company's engineering leadership understood that Japanese machining centers existed and that they were cheaper. What Cincinnati's leadership believed with justification based on the evidence available in 1975 was that the achromatic controller's market penetration, the dealer network's application engineering capability, and the mechanical quality of Cincinnati's equipment constituted an advantage that price alone could not overcome. American shops had invested in achromatic training. American machinists spoke achromatic. American plant engineers trusted Cincinnati application engineers in ways they did not yet trust a Japanese builder's factory direct technical representative who had been in the American market for 18 months. The belief was not irrational. It was, however, time-limited, and the clock was running faster than Cincinnati's leadership understood in 1975. By 1980, Japanese builders held over 30% of the American CNC machining center market. The NMTBA statistics for that year were not a footnote. They were a verdict in progress. Cincinnati Milacron's strategic response to the Japanese price pressure took two forms. The first was the expansion into industrial robots and plastics processing equipment that the T3 program had initiated in 1974. The logic was defensible if the machine tool market was under irreversible price pressure from Japanese competition move engineering resources and corporate investment toward markets where American technology leadership could be maintained. Robots, injection molding machinery, manufacturing systems integration, markets where the price per unit was higher, the Japanese competition was less established, and Cincinnati's engineering capability could create a defensible position. The pivot was not wrong in principle. In execution, it created a resource allocation problem that Cincinnati Milacron was never able to fully resolve. Every dollar of engineering investment directed toward the T3 robot program, toward plastics processing equipment development, toward manufacturing systems. Integration was a dollar not directed toward the achromatic CNC controller, the system that was simultaneously being challenged in the American market by a Japanese controller that was cheaper, simpler, and increasingly better supported in American training programs. The achromatic problem deserves its own accounting because it is the most painful paradox in Cincinnati Milacron's history, more painful even than the LBO that ended the company because the LBO was inflicted from outside. The achromatic problem was structural, and it developed from inside the very advantage that the achromatic had created. By the late 1970s, Fanuc, the Japanese CNC controller manufacturer founded in 1972 as a spin-off of Fujitsu, had achieved something remarkable. It had built a CNC controller that was reliable, programmable, and priced at approximately $8,000 installed. Cincinnati Milacron's achromatic, with its more sophisticated capability and its extensive American field support infrastructure, was priced at approximately $18,000. The price differential was significant, but price alone did not explain what happened next. What happened next was that Fanuc's programming language, the G-code and M-code structure that Fanuc had standardized across its controller product line, began appearing in American community college machining technology curricula, not because community colleges had made a strategic decision to favor Japanese technology, because FANUC had made its programming language available, had published its documentation widely, and had priced its training materials at a level that educational institutions could afford. Achromatic programming was proprietary. Its documentation was controlled. Its training was provided by Cincinnati's own application engineers at Cincinnati's schedule and at Cincinnati's cost. A machinist graduating from a 2-year machining technology program in Ohio in 1981 knew FANUC. He might never have seen an achromatic panel. When that machinist went to work in an American job shop, and when that job shop needed a new CNC machining center, the shop foreman's specification conversation with the Cincinnati machine tool dealer took a turn that Cincinnati's sales organization had not fully anticipated. The foreman wanted the Cincinnati machine. He trusted the Cincinnati machine, but he wanted FANUC controls, because his machinists knew FANUC, because retraining on achromatic cost time and money that a job shop operating on thin margins could not easily absorb, because the next machinist he hired would know FANUC and the one after that. The specification sheet problem that opened this story, the Detroit plant engineer writing FANUC on a Cincinnati order form in 1985, did not begin in 1985. It began in the machining technology classrooms of American community colleges in the late 1970s, where the next generation of American machinists was learning to program on a Japanese controller because the Japanese controller's documentation was available and the American controller's was not. Cincinnati Milacron responded. The company developed achromatic versions with improved G-code compatibility with interfaces that reduced the programming distance between achromatic and FANUC syntax. The engineering effort was real and the results were genuine, but the response was reactive. The standard had already shifted. The machinists had already been trained. The purchase orders were already being written with FANUC on the controller line, and simultaneously operating on an independent timeline that intersected with the controller problem at the worst possible moment. The Japanese machine tool builders were not standing still on price. In 1981, a Yamazaki Mazak Quick Turn 10 CNC turning center entered American distribution through Mazak's expanding American dealer network at $44,000. The Cincinnati Milacron equivalent, the Milacron No. 5 CNC turning center, was priced at $89,000. The Mazak came standard with a FANUC controller. The Milacron came with an achromatic. The job shop foreman who had bought Cincinnati for 30 years looked at the specification sheet, looked at the price difference, and did the arithmetic that his margin required him to do. The Mazak was not an inferior machine. It was a different machine, built to different tolerances with different long-term durability characteristics with a field service infrastructure that was still developing in the American market in 1981. A Cincinnati application engineer who had been in the territory for 15 years knew things about process engineering and fixturing and tooling selection that the Mazak factory representative was still learning. That knowledge was real. It was worth something. The question was whether it was worth $45,000. For a growing number of American job shop owners in 1981, operating in an economy that had been through the oil shocks of 1973 and 1979, facing the deepest manufacturing recession since the 1930s, the answer was no. The NMTBA statistics for 1982 were not a trend line anymore. They were a collapse. American metal-cutting machine tool shipments, which had peaked at $5.7 billion in 1980, fell to $3.1 billion in 1982. Japanese builders in the same period increased their American market share to over 40% of CNC machining centers. The manufacturing recession that had begun in 1979 had not created the Japanese advantage. It had revealed it. When American factories cut capital equipment budgets, they cut the expensive machines first. The Cincinnati at $89,000 waited. The Mazak at $44,000 moved. Cincinnati Milacron's revenue fell from $1.2 billion in 1978 to approximately $900 million by 1982. The Columbia Parkway workforce began contracting. Engineering programs were prioritized and reprioritized. The robot division, the plastics machinery division, the machine tool division, each competing for the engineering investment that the company's declining revenue base could no longer fully fund across all three simultaneously. The American machine tool industry, collectively through the NMTBA, filed a Section 201 trade petition with the U.S. International Trade Commission in 1983. The petition argued that Japanese machine tool imports supported by MYTI coordination and export pricing constituted an unfair trade practice that was causing material injury to the American industry. The legal mechanism existed. The argument was documented. The NMTBA's statistical evidence was extensive. President Reagan declined to impose tariffs. Instead, in 1986, the Reagan administration negotiated voluntary restraint agreements, VIVR, as with Japan and Taiwan. The VRAs capped Japanese machine tool imports at 1981 levels for a period of 5 years. They were not tariffs. They were a ceiling on a flood that had already reshaped the American market. Japanese builders who had been gaining share annually since 1975 were now constrained at their 1981 position, a position that already represented over 40% of the American CNC machining center market. The VRAs slowed the advance. They did not reverse it. And while the trade petition moved through Washington, the fifth force arrived. Korean machine tool builders, Hyundai Kia Machine Tools, Daewoo Heavy Industries, Doosan and Taiwanese builders, YCM Victor Taichung Femco, entered the American market in the mid to late 1980s with vertical machining centers priced between $28,000 and $45,000. These were not the precision instruments that Cincinnati Milacron built. They were not the mechanically sophisticated machining centers that Mazak and Okuma offered. They were adequate machines, adequate for the facing drilling and light milling operations that constituted the majority of American job shop work at prices that made the Japanese machines look expensive. The surviving American builders had spent the first half of the 1980s trying to compete with Japanese pricing. They could not. They had spent the second half trying to move upmarket to the high-precision, high-speed, high-complexity work where American engineering advantage could justify American pricing. The Koreans and Taiwanese arrived in that moment and eliminated the middle of the market entirely. There was no price point at which an American builder could now compete on cost. The market had two segments: commodity machining centers from Korea and Taiwan and high-precision machining centers from Japan and Germany. American builders were priced above the first and increasingly below the technical reputation of the second. In 1991, Cincinnati Milacron made a decision that its management believed was a consolidation strategy and that history has evaluated as a critical overextension. The company acquired Kearney and Trecker Corporation of Milwaukee, Wisconsin. Kearney and Trecker was not a minor acquisition. It was Cincinnati Milacron's oldest and most significant American rival. The Milwaukee company that had invented the automatic tool changer in 1958, that had built the Milwaukee Matic Machining Center that defined horizontal machining center practice in American industry for 2 decades, that had itself been through a hostile acquisition by Cross and Trecker in 1978, and had emerged from that transaction with its engineering staff reduced and its product development pipeline thinned. The logic of the Cincinnati K&T combination was market consolidation. 2 weakened American builders combined might achieve the scale and the cost structure to compete against Japanese builders who were individually larger than either American company. The combined entity would control a broader product line, a larger dealer network, more complete coverage of the American machining center market. The reality was debt. The acquisition loaded Cincinnati Milacron's balance sheet at the moment when the company's revenue base was least able to service it. The K&T Milwaukee engineering staff, already reduced from its peak, was further reduced in the integration. The Milwaukee Matic product line was discontinued. The Milwaukee Facilities Transfer Line division, which had produced the large format machining systems that American automotive and aerospace manufacturers used for complex structural components, was rationalized into Cincinnati's own transfer line operations and then contracted as automotive procurement, continued its long withdrawal from American machine tool suppliers. The sentences get shorter here, because the events get faster. 1992. Cincinnati Milacron's annual revenue falls below $600 million. The Columbia Parkway workforce is below 8,000. 1993. The Plastics Machinery Division, the most profitable segment of the company's business, is separated into a distinct operating unit. 1994. The Robot Division. The T3's successor programs is restructured. 1995. The Achromatic CNC Controller Development Program receives its last significant engineering investment. 1996. Cincinnati Milacron reports a net loss. 1997. The company is taken private in a leveraged buyout. The acquiring entity is a financial buyer. The transaction is valued at the company's asset liquidation price, not at any premium for its engineering capability, its brand equity, or its institutional knowledge. The company that had introduced CNC machining to American industry in 1960 is purchased in 1997 for what its buildings and equipment are worth. The Achromatic program is terminated. The new entity is renamed. Not Cincinnati Milacron. Unova Incorporated. The Cincinnati is gone from the name. The Mill Creek Valley is gone from the identity. What remains is a holding company managing the remaining divisions of what had been the largest machine tool builder in America. The Columbia Parkway campus employment falls below 2,000, then below 1,000. The machine tool dealer network, the 200 American firms that had represented Cincinnati Milacron across the country, that had provided the application engineering infrastructure that no Japanese builder could replicate in the American market before 1980, had been contracting since the mid-1980s. By 2000, most are gone. Not acquired, not consolidated, gone. The principals retired. The technical staff dispersed into other industries. The knowledge, the accumulated process engineering expertise of 200 organizations built over 40 years specific to Cincinnati machines and Cincinnati applications does not transfer. It dissipates. The Achromatic programmers, the American machinists who had learned Cincinnati's proprietary CNC language, who had spent careers writing programs on Achromatic panels in American shops, have no successor market for their skill. The language is dead. The panels are being replaced. Some retrain on FANUC. Many are at an age where retraining is less available than retirement. The machine tool rebuilder community, the American industrial trade that had extended the working life of Cincinnati machines by disassembling them, rescraping their ways, regrinding their spindles, and returning them to original tolerance, collapses with the dealer network. When a new Korean vertical machining center costs $32,000, the economics of rebuilding a Cincinnati knee mill at $18,000 in labor and parts no longer work. The rebuilders close. The hand-scraping skill, the craft of restoring a machine's precision surfaces by hand, a technique that required years of training and produced accuracies that grinding alone could not achieve, disappears from American industry faster than anyone bothered to document it. The professional categories are vanishing. The application engineer, the Achromatic programmer, the machine tool rebuilder, the Cincinnati dealer's technical sales representative, the NMTBA certified machine tool inspector who measured spindle runout with a tenths reading test indicator against a granite surface plate. These are not job titles. They were careers. They had apprenticeships, professional associations, 40-year trajectories. They did not retire into equivalent work. The work no longer existed in America. The company is gone. The machines are not. In job shops across Ohio, Michigan, Indiana, and Pennsylvania, in the industrial geography that Cincinnati Milacron supplied for a century, Cincinnati milling machines are still running production. Not as museum pieces, not as curiosities, as working machines making parts to print, holding tolerance on jobs that their owners could route to a newer machine but choose not to, because the Cincinnati does it correctly and has been doing it correctly for 30 years and gives no indication of stopping. A Cincinnati Milacron No. 3 knee mill in running condition sells on eBay today for between $2,000 and $6,000. It sells within weeks. The buyers know exactly what they are buying. They are not buying nostalgia. They are buying a machine that was built to a standard that the price of its replacement does not replicate. They are buying cast iron ways ground to 0.005 per foot. They are buying a spindle that someone in Cincinnati fitted by hand to a 1/10,000th of an inch of runout. They are buying 40 years of demonstrated reliability at a price that reflects the market's assessment of what demonstrated reliability is worth, when the alternative is a $32,000 Korean machining center whose long-term durability has not yet been demonstrated by 40 years of production use. The Cincinnati Toolmaster knee mill, the lighter, more versatile variant that Cincinnati Milacron produced for toolroom and educational use, sells in the same range and to the same buyers. Community college machine shops in Ohio and Michigan still run them. Students learning to machine on a Cincinnati knee mill are learning on equipment that their instructors learned on. The pedagogical continuity is accidental. The machine simply refuses to become inadequate. On the Practical Machinist Forum, Practical Machinist. The online community where American machinists discuss, diagnose, troubleshoot, and preserve vintage American machine tools, the Cincinnati Milacron threads run long. The achromatic controller troubleshooting discussions are among the most technically detailed in the forum's archive. Machinists who are keeping 1980s-era Cincinnati CNC machining centers running in 2024 are doing so by reverse engineering replacement parts, by sharing ladder logic diagrams, by locating obsolete electronic components through industrial surplus channels, by applying to a 40-year-old controller the same diagnostic discipline that their predecessors applied to the machines themselves. The knowledge that Cincinnati Milacron's engineering department once maintained and distributed through its field service organization is now maintained and distributed by the machinists themselves voluntarily on a forum for free. The vintage machinery website VintageMachinery.org holds scanned copies of Cincinnati Milling Machine Company catalogs dating to the early 20th century. Parts books, maintenance manuals, engineering drawings. The documentation that a machine tool company produces over 113 years of operation and that would otherwise be lost when the company ceases to exist is preserved in a digital archive maintained by volunteers who understand that a machine without its documentation is a machine that cannot be fully understood or correctly maintained. The American Society of Mechanical Engineers has recognized specific Cincinnati Milling Machine Company products as historic mechanical engineering landmarks. Formal acknowledgement that the machines represent a contribution to American engineering practice significant enough to warrant institutional preservation. These are the communities that remember. Not officially, not with endowments or government programs, with time, with expertise, and with the specific kind of care that people extend to things they understand to be irreplaceable. Now for the footnote that the revenue charts and the trade statistics do not contain. The Cincinnati Milacron T3 industrial robot, the machine that was the first commercially sold industrial robot in American history, introduced in 1974, purchased by General Motors for body welding operations. The product that represented Cincinnati Milacron's most far-sighted strategic decision and its most complicated resource allocation problem is today on permanent display at the Smithsonian National Museum of American History in Washington, D.C. Consider what that means. The artifact that the nation's Museum of History chose to preserve, the object that the Smithsonian Institution determined was significant enough to place in permanent collection alongside the Star-Spangled Banner, and the Wright Flyer is not a Cincinnati milling machine. It is the robot. The product that Cincinnati Milacron built when it looked at the trajectory of American manufacturing and decided to build the factory of the future is the product that history remembered. The milling machines, the product that defined the company for 80 years, that equipped American factories from the Springfield Armory to the Boeing Wichita plant to the Pratt & Whitney engine facility in East Hartford, are in job shops, on eBay, in community college machine rooms, running production. The robot is in the Smithsonian. There is something in that inversion that captures the Cincinnati Milacron story more precisely than any revenue chart. The company that built American manufacturing's past and that tried to build its future is remembered for the future. It tried to build, not for the past, it actually built. The past is still running. Nobody put it in a museum. It was too busy making parts. What is gone, what cannot be found on eBay, cannot be preserved on a forum, cannot be reverse engineered from a spare parts diagram, is the human infrastructure that surrounded the machines. The Columbia Parkway campus on Cincinnati's eastern edge still stands. Some of the buildings have been converted. Some have been demolished. The address that employed 15,000 Americans at its peak, that generated $1.2 billion in annual revenue in 1978, that sent Cincinnati Milacron machines to Boeing and Pratt & Whitney and General Motors and the U.S. Air Force, that address is quieter now than it has been since the Mill Creek Valley's first factory opened in the 19th century. In a tool and die shop in a suburb east of Cincinnati, close enough to Columbia Parkway, that on a clear day you could see the water tower, that still carries the Cincinnati Milacron name in faded paint, There is a Cincinnati Milacron number 3 milling machine serial number cast into the column in 1971. The coolant pump runs, the spindle turns, the table moves in X moves in Y, presenting the workpiece to the cutter with the same precision it presented workpieces to cutters in 1971, in 1981, in 1991. The chip comes off clean. The part comes off to print. The nameplate still says Cincinnati, Ohio. The company that put it there has not existed for 25 years. Every week we tell the stories of the American companies that built the machines the factory ran on and what the market, the trade statistics, and the decisions of men in boardrooms and financial institutions did to them. If that history matters to you, if you ran one of these machines, set up a job on one, learn to read a dial indicator against one spindle, subscribe. Leave a comment with the Cincinnati machine. You ran the shop, you ran it in the city it was in. The next story is already waiting. And it begins like this one on a factory floor in America, with a machine that held tolerance in a company that no longer exists in a city that is still there.